Okay, starting to get some good numbers there. You all set to go, man?
Ready to go?
I can't hear you.
Okay, so thanks, Ben, and Daniel and the other organisers for the opportunity to speak.
Still no sound there.
You can't hear me? That's strange.
I can hear Matthew very good.
Okay.
Ben, how about you?
Loud and clear. So I think it's just Ben that can't hear me for some reason. In that case, maybe
it's good sound.
Now I hear you. Yeah.
Okay.
Very good. Okay.
Okay, so let me try again. Maybe I'll get going, and if there are any issues, just please shout out and stop me. Okay, so thanks for inviting me to speak. It's good to be part of the seminar, figuratively, if not all in the same place. So I want to talk about the atomic structure of ancient grain boundaries today. So let me begin with a quick overview of Democritean atomism. So you've all probably seen some of these ideas before. So the Greek atomists believed that all of the phenomena that exist in the world is due to the coming together of atoms and void. They believe that atoms, the fundamental building blocks, are indivisible. Atom, of course, comes from the Greek word atomos, meaning uncuttable. Atoms are also eternal, they last forever, they're indivisible, and everything that we observe is the result of atoms coming together in different configurations. So why am I presenting a sort of dodgy overview of Greek atomism? Well, the reason is that the picture I want to present to you today of ancient mean curvature flow has a very similar picture with the Grim Reaper solution to curve shortening flow playing the role of atom. So we're going to have sort of a fundamental building block for all ancient solutions, at least those contained in slab regions. Okay, so let's recall the simplest mean curvature flow is the curve shortening flow. So here we look at curves in the plane, which evolve with pointwise velocity equal to their curvature vector. And this theorem here says that the only convex ancient solutions, so the only convex solutions which have existed for all negative times, are these four. So we have the stationary line up here, the shrinking circle, the Anganant oval, bottom left here, and we have the translating Grim Reaper solution to the right. Okay, so the Grim Reaper solution simply translates to the right under the flow. We can ignore the stationary line solution. We can just focus on strictly convex examples. And the shrinking circle solution, we're not going to be interested in either, because this solution has the property that it's entire. It sweeps out all of space. We're going to be more interested in these other two solutions here, which sweep out strip regions. And in fact, this behavior is a dichotomy. So it's known that a convex ancient solution to mean curvature flow either passes through all points in space, either sweeps out all of space, or it's confined to a slab region between two parallel hyperplanes. So that's the curve shortening flow. The picture is very well understood there. So let's take a closer look at the Anganant oval. So the Anganant oval decomposes into two Grim Reapers in a very specific way. So if you look at the two sort of tips here, so if you focus on these points which have a fixed normal direction, say take the horizontal normal directions, and we space-time translate the flow so that that normal direction, so that the point with that normal is at the space-time origin, and then take s to infinity. What we're going to see on the left side, we're going to see this converging to a Grim Reaper, moving to the right with speed 1. And if we do the same game to the point p minus, we're going to see a Grim Reaper moving to the left with speed 1. And so the point here is not just that this decomposes into 2 Grim Reapers, it decomposes into 2 identical Grim Reapers. Well, or rather equal and opposite Grim Reapers. So you cannot get this sort of picture at the bottom where you have a sort of a fat, slow Grim Reaper moving to the right, joining together with a sort of thin, fast Grim Reaper moving to the left. So there's some kind of restriction on what configurations are allowed here. Okay. In higher dimensions, there's this nice family of translating solutions to the curve shortening flow in R3 called the flying wings. And these guys are a family of convex translators, W theta, parameterized by theta in between 0 and pi over 2. These translators, so you can see a picture of one here in the top left, they translate vertically with speed 1 over cosine theta, and they make the same angle. So that's this angle here with the horizontal plane. And they're asymptotic to 2 Grim planes on each side, which make the same angle theta with the horizontal plane. Okay, so here to the right, you see a Grim Reaper tilted with positive angle theta, and on the left, you see one tilted with negative angle theta. And these flying wings are somehow an interpolation between the 2. And there's a theorem which says that these are the only examples which lie in slab regions. And so once again, we see that only certain configurations are admissible. You can't have a sort of a large angle on one side with like a fat Grim Reaper, and a thin angle on the other side with a smaller Grim Reaper. So you have some kind of balancing between what you see here. And I want to mention a recent result. I think last week, Yi Lai posted a preprint on the archive with a very nice construction of an analogous family of steady Ricci solitons for Ricci flow. So the picture is very similar. And yes, so that solved a conjecture of Hamilton, I believe. So you get a similar picture in Ricci flow as well. In higher dimensions, you get the same kind of family, but with an added rotational symmetry. So you get a rotational symmetry. So you get instead of just getting 2 Grim planes, you get a whole sphere of Grim planes that they're asymptotic to. And similarly, there's a higher dimensional version of the Angenant oval under a rotational symmetry hypothesis. So this one looks like kind of like a rotated Angenant oval. So that's another example in higher dimensions. And these examples, again, there's a uniqueness theorem for these examples, assuming these rotational symmetry conditions. And so once again, so you can analyze these examples, and you only see certain configurations of Grim planes at the edges. So again, you only get certain allowable configurations, at least under this rotational symmetry hypothesis. And this particular example, the rotationally symmetric ancient pancake solution, this one here, this one's going to play a major role in constructing additional solutions. So these were the only examples known so far which lied in slab regions. And if we combine these with the family of ancient ovaloids, which are a family of entire solutions, then that was the only known examples of convex ancient solutions to mean curvature flow. Okay, so the ancient pancake is going to be one major tool in analyzing these ancient solutions. The next main tool is going to be the differential Harnack inequality. So the differential Harnack inequality of Hamilton, it's equivalent to this first statement that the family of support functions. So you look at these family of convex hypersurfaces. So they have an associated, so each hypersurface has an associated support function. So for each normal direction in Sn, the support function gives you the distance of the corresponding supporting hyperplane to the origin. And the differential Harnack inequality tells us that this family is concave with respect to t. As long as the solution is ancient, this family will be concave with respect to t. And so this is going to be a very, very powerful property, which we're going to use a lot. Since the time derivative of the support function gives us the normal speed in that normal direction, or of the point, sorry, with that normal direction, we get monotonicity of the speed. So in particular, this limit exists. So we can take the limit of the speed in a fixed normal direction as time goes to minus infinity. Similarly, just by concavity, we get a limit for the support function after scaling by minus t. And again, just exploiting the concavity, we find that these two limits must be equal to each other. And then, well, it's not too hard to see that once you have limits for the rescaled support functions, you actually get a limit for the rescaled bodies. So these omega sub t's are the convex regions bounded by the time slices. So since the scaled support functions converge, you can sort of show that the rescaled bodies converge as well. And you also find that the limit of the rescaled support functions is the support function of the limit of the rescaled bodies. Okay, so these are some of the main things you get from the differential Harnack inequality. And in particular, this body, this limit of these rescaled bodies, m sub star, is particularly important, or rather particularly useful. So we give it a name. We called it the squashdown of the ancient solution M. We'd be open to any other suggestions for names of this. If anyone has some good ideas, please share that in the chat. But this guy's going to play a fairly important role. Note that it's not the same as the blowdown. So the blowdown is another concept which arises for ancient solutions. And for the blowdown, you scale by the square root of minus t. And in the limit, the blowdown gives you a shrinking solution, but the squashdown does not. And in fact, it just gives you it'll give you a convex body which lies in a Euclidean space of one dimension lower, because this scaling kills the bounded direction. Okay, but this squashdown tells us a lot about our ancient solution. So let's have a look at some squashdowns of some familiar solutions. So let's look at the Grim Reaper. The Grim Reaper, the Grim Reaper moves with constant speed. So its displacement is precisely 1 times, so the speed is 1, its displacement is t. So when we scale by t, the displacement of the tip, so the tip becomes stationary, but the bounded direction becomes crushed down or collapsified, as Glenn just suggested. And we just get a half line for the Grim Reaper. Similarly, the Grim hyperplanes. So the Grim hyperplanes will give you, instead of half lines, will give you half spaces, higher dimensional half spaces. The Unguent oval, we saw that that's the interpolation of two Grim Reapers, and you can see that its squashdown reveals that. So it's the intersection of two oppositely oriented Grim Reapers. The ancient pancake, you see the same picture. So the ancient pancake really looks like an S1 of Grim Reapers, and that's revealed by the squashdown. And same thing for the flying wings. They look like the intersection of two Grim planes, or an interpolation of two Grim planes, and we see that we get the intersection of two half spaces here, appropriately configured. So the two half spaces support the unit sphere. Okay, so we only get a circumscribed wedge there. Okay, so that's some examples. Another thing that the Harnack inequality tells you is that you always get asymptotic translators. So we saw how to get asymptotic grim reapers for the Ungenant oval. Well, this process works in general. If you take a sequence of normals and times, with the times going to minus infinity, space-time translate so that that point goes to the space-time origin, then the Harnack inequality allows you to take a limit, and it shows you that you get a translating limit, and it also tells you that that's related somehow to the squashdown. Okay. A very nice consequence of this, which makes this useful for solutions which lie in slabs, is that you immediately get that the limit of the mean curvature is non-zero in most directions. Okay, and the reason is that if you had, say, a point, maybe I can draw this on here. So if you look at, say, some point here, and you do the space-time translation, so that this point goes to the space-time origin and take a limit. Well, if the mean curvature of this point, if the speed was going to zero, then the limit translator you would get would be this plane. But this plane, this plane is transverse to the slab, which is impossible because the solution always lied in the slab. So the only directions which give you zero speed in the limit are the vertical ones. So this is very, very helpful. I should remove that. There we go. Okay, so that's the asymptotic translators. So those are our main tools. And the first thing we want to do with them is construct some new examples. And so what we do here, so the most basic construction. So you give me a regular polytope P, okay? Then I can, or we rather, I didn't mention that this is joint work with Theodora Borni and Giuseppe Tenaglia. So if you give us a bounded regular, sorry, not bounded, if you give us a regular polytope P, we'll give you a convex ancient solution to mean curvature flow with squashdown equal to P, okay? And this solution is going to lie in a slab of width pi divided by the in radius of the polytope. So you might as well scale so that the in radius is 1, and then you get solutions which sweep out a slab of width pi, and they're constructed in such a way that they're reflection symmetric across the midplane of this slab. And as you expect, they will inherit the symmetries of P. So P is a regular polytope, so it has dihedral symmetries. So these solutions have the same symmetry groups plus the reflection symmetry across the mid-hyperplane. Furthermore, so on the left here, you have a bounded regular polytope. So that gives us a compact ancient solution. But we can also look at unbounded regular polytopes, and those are cones. And it turns out that the solutions we get from them are translating solutions to the flow. So we get a big family of compact ancient solutions and translating solutions. Well, not a huge family, but we get a family of them. And I just want to mention as well that we can also say something about the asymptotic translators. So it turns out that if you look at an asymptotic translator, in say we look at some normal direction at this vertex, then if we look at the asymptotic translator, okay, then that's going to give us a translating solution. In particular, that's an ancient solution, so we can look at its squashdown, and the squashdown of the translator you get is going to be the clear that. The squashdown that you get is going to be the support cone. Not sure why this is not working. There we go. Is going to be the support cone of the squashdown to the ancient solution at that point. So this is a terrible picture, but you get the point. I won't be able to go too much into that anyway, because there's not so much time. So let's, okay, so that gives us an example for every regular polytope. But that's not so many examples, because in dimensions at least 5, there are only, I think, three bounded regular polytopes of each dimension. So we wanted to construct more examples. So we looked for non-regular examples, and we were able to cook up ancient solutions for any simplex. So that now gives us an uncountable infinite family of solutions. So we don't. So if the polytope is a simplex, then we don't need it to be regular. And indeed, we also get unbounded examples. So a bounded simplex will be the usual notion of a simplex, but essentially an unbounded simplex will be a cone over a bounded simplex. So we also get an infinite family of translators in that case. Okay, so we'll see why that is in a second. So let me show you how to construct these examples. So as usual in these kind of constructions, if you want to construct ancient solutions, you generally want to take a limit of old but not ancient solutions. Okay, and our old but not ancient solutions are constructed as follows. So let's look more generally at any circumscribed polytope P. Okay, so you give us a circumscribed polytope P. That's just a convex set which can be written as the intersection of finitely many half spaces which support the unit sphere. Okay, so you just take a finite number of unit vectors and look at the intersection of the corresponding half spaces. And we can look at bounded and unbounded examples. And now, so these guys are going to be living inside of Rn. And so now we put this guy as the midplane of a slab in Rn+1. And then along each of the edges, we place a Grimm hyperplane. Okay, so now instead of having just, say, in the two-dimensional case, just a line here, you place a whole Grimm hyperplane along here. And my hand is not very steady, but I think you see the point. So you make all of these guys, you replace these half spaces by Grimm hyperplanes. Okay, and then you take the intersection of all of these things and you end up with a convex body, which we call MR, as long as we make this distance equal to R. Okay, so we replace all of these guys by Grimm hyperplanes, and then we move them out to a displacement R from the origin. And for each R, that gives us the boundary of a convex body, which we call M sub R, sorry, superscript R. And so what we're going to do is we're going to evolve this thing by mean curvature flow to get an old but not ancient solution, and then try to take a limit as R goes to infinity. And I guess the picture that I'm trying to draw here is that, so in the same way that you think about half spaces in the field of convex geometry, you can sort of think about Grimm hyperplanes for this theory of ancient solutions. So you replace half spaces by Grimm hyperplanes. Okay, so since these surfaces are boundaries of convex bodies, sort of general nonsense allows us to flow them by mean curvature flow. We get solutions which are smooth and locally uniformly convex at interior times, and we get sort of the best possible convergence up to the initial time. And that's pretty standard in the compact case. In the unbounded case, we need to work a bit harder, and we use a sort of doubling argument, which was, I should give credit to Brett Kochwa for suggesting that to us. And the idea is that you just choose a sort of unbounded direction, and then you cut off at a certain height, and then double the solution across that height, and then you get a compact thing which you can flow by mean curvature flow, and then you take a limit as this height goes to infinity to get an unbounded thing. So that's a nice trick, which you can use in the unbounded case. And then the first thing you want to show is that these things, as R goes to infinity, last for arbitrarily long times. And that's pretty easy to show using barriers. So by putting an ancient pancake on the inside and the initial Grimm hyperplanes on the outside, you see that the time taken for this solution to pass through the origin takes time approximately R. So you get that there. And so then what we do is we just translate in time, but not in space, translate in time so that the origin is reached at time 0. And so then you have family of solutions which are defined on ever increasing backwards time intervals and which pass through the origin at time 0. So if we can indeed take a limit of these things, we get an ancient solution that passes through the origin at time 0. Okay. Oop. Okay, so how can we take a limit? So the next tool we need is something I'm going to call a faux Harnack inequality. And the idea is as follows. So we notice that on the initial configuration of, well, we've got Grimm hyperplanes. And so it's very easy to check that because these guys are translators and, well, because they're Grimm hyperplanes explicitly, you can show that this inequality holds on the initial condition. So the mean curvature at the point whose normal direction is z is at least the inner product of z with v for every vertex of the initial polytope. But both sides of this equation satisfy the linearized flow. So you can take the difference of the two and apply the maximum principle, and you get that this inequality is preserved under the flow. You have to work a little bit harder in the non-compact case, but you essentially get it preserved for all of the compact approximating ones, and then take the limit. So that works in the unbounded case as well. And then you get this inequality here, which is what I'm going to call the faux Harnack inequality. So you note that the maximum of these inner products over all the vertices is actually the support function of the polytope P. And I'm calling it a faux Harnack inequality because this is exactly what you would get from the Harnack inequality if these solutions were ancient and their squash down was P. So we saw that already. And so this is going to serve as a kind of replacement for the kind of things you would do with the Harnack inequality. In particular, if you integrate this guy, so the time derivative of the support function is the negative of the mean curvature. So you integrate this, you get this bottom inequality here. And in particular, this ensures that the squash down of the limit solution, if it exists, certainly contains the polytope P. So that's one tool. We still need to be able to take a limit. In order to be able to take a limit, it really just suffices to have a uniform in our lower bound for the in radius of the time slices, because then we can just take a limit as convex bodies and apply the mean curvature flow regularity theory. So as long as you have a uniform in R lower bound for the in radius. In order to get that, we do it in 2 steps. So we again look at the initial data, and we see that the initial configuration has a nice width estimate. So this W sub R is the width transverse to the slab, orthogonal to the slab. And the initial condition satisfies this nice width estimate. It says that wherever the mean curvature is small, the solution is close to the boundary of the slab. Sorry, the surface is close to the boundary of the slab. And a maximum principal argument, which is motivated by an argument of Spruck and Schau for translators, shows that this estimate is preserved under the flow. So we get this for positive times. And so then all we need to do is show that the mean curvature is quite small on sufficiently large sets. And that's a bit trickier, so I can't give you all of the details of that. But the idea is to use the pancakes, use the ancient pancake as a kind of barrier, a comparison solution, and we also require the faux Harnack inequality, and that gives us this nice estimate here, which basically says that the mean curvature is very small on a ball of uniform size about any point which is a long way away from the edge. Okay, so if it says that if you're not very close to the edge, then the mean curvature is actually very small. And so the in radius bound follows. And in fact, you also get that the width stays close to pi. So we can now take a limit. We get a limit ancient solution. We know that this solution lies in a slab of width pi, but no smaller slab by the width estimate. And by the faux Harnack inequality, we know that its squash down contains the polytope P. So we've got one step left, is to show not just that it contains the polytope P, we want to show that it's equal to. So we want to rule out something like this happening, where this initial edge that you started off with somehow wanders off as R goes to infinity. and move somewhere else. So we want to keep the faces, we want to stop the faces from wandering off. And how do we do that? Well, let's suppose that you have something like the following picture. So suppose that you have your initial polytope as this pentagon. And as r goes to infinity, you look at mr of t scaled by t. And suppose that you have, well, this is a regular one. So suppose that all of the faces are sort of moving away from the sphere of radius 1. Well, if you look at the ancient pancake solution and rescale by t, and you look at its cross section, that's going to converge to the circle of radius 1. So if this situation was happening, you would see that the cross section of the ancient pancake was lying strictly inside of the edge region of your old but not ancient solution. But by the way we've constructed the old but not ancient solutions, they reach the origin at time 0, as does the ancient pancake. But then the avoidance principle tells you that they have to intersect at all earlier times. Okay, so this isn't quite a contradiction yet, because that intersection could be happening close to the boundary of the slab. So you have to work a little bit harder and to show that you don't get an intersection anywhere else, which then is a contradiction with the avoidance principle. So that completes the proof for regular polytopes. You have to work a little bit harder for simplices. What you do is you just sort of play around with the center of the ancient pancake, and the same kind of argument tells you that Sn minus 1 is an inscribed sphere for your squash down. And so then that's enough to get the result for simplices. And that completes the proof in those cases. And note that this is the only step where we needed to restrict to regular polytopes or simplices. Okay. Okay, so all of those examples we constructed. So we looked at circumscribed polytopes, and then we were able to get solutions for regular polytopes or simplices. So we're also able to prove that in general, the squash down of any ancient solution is necessarily a circumscribed convex body. So that's what this theorem says. So in particular, you can't get a picture like this where some edge is not tangent to the sphere. So you always have to get something which is circumscribed. Yeah. So I won't be able to go into the proof of that, but once again, it involves barrier arguments using the ancient pancake, and of course the differential Harnack estimate. So it's not too bad, but it's kind of a delicate argument. And a crucial aspect of that argument is to get a width estimate all the way up to the boundary. The first thing you need to do is to show that the width of the solution is approximately pi all the way up to the edge region. Okay. So I won't go into that, but what you see here is important. So you get that the squash downs. So this gives us a necessary condition for being able to construct an ancient solution in this way. We believe it's also sufficient, but we could only get them so far for regular polytopes and simplices. And in one other setting. So I guess in the last 5 to 10 minutes, I'll talk about this other situation where we're able to construct ancient solutions. So here, what we're able to do is say, well, if you give us a circumscribed cone, C, okay, so we have this circumscribed cone, C, then we're going to give you a convex eternal solution to mean curvature flow, whose squash down is the circumscribed truncation of that cone. So you truncate the vertex in such a way that your convex body is still a circumscribed polytope. And we're able to give you an eternal solution with this property. But since the squashdown of any convex translator is always a cone, this thing cannot evolve by translation. So these examples are counterexamples to a conjecture of White. So White conjectured that any convex eternal solution to mean curvature flow necessarily evolves by translation. These examples are eternal, and since their squashdown is not a cone, they cannot possibly be translators. So let me talk in the last few minutes about the proof of that result. So the first step, well, we go back and we construct our old but not ancient solutions as we did before. So we look at the suitable configuration of Grimm planes. We evolve them by mean curvature flow. And we're going to choose a time normalization in a different way than we did before. So what we first note is that using, once again, barrier arguments and the faux Harnack inequality. So by placing ancient pancakes above our solutions, we find that they exist for all time. Using the faux Harnack inequality, we can take forwards limits. So here we can actually take a limit as s goes to plus infinity. So again, that's because, well, this is using the faux Harnack inequality. And we can take a limit as s goes to plus infinity of this guy. We also get a relationship between those two limits. And that allows us to deduce the following. So we also get then a limit, so a forwards limit for these rescaled bodies. And we can see what it is. So let me try and explain what that is. So in order to write down what that forwards limit is, you look at the backwards limit. That's our polytope P. And you take each of the supporting half spaces, the half spaces which support the sphere, and then you translate them so that instead of supporting the sphere from the outside, instead of the sphere supporting from the inside, you translate them so that they're on the outside of the sphere. So the same with this one. Oh, that's not a very straight picture. So you move that guy so that it supports from the other side, and same with this one. You translate so that it supports from the other side here. Okay, and that defines the forwards limit. And notice that when you do it with this one here, you actually lose. So this one doesn't actually contribute to the intersection. Okay. So that's the first step, and this is going to tell us some useful information. So the first thing that tells us is that, well, if you look at the point whose normal direction is in the direction of the vertex of the cone, well, at time 0, the mean curvature of that point is 1 by construction. But by these considerations here, the mean curvature as t goes to infinity is going to be this distance. Okay, that's just this equation. But that distance is going to be equal to, so by this final thing, that distance is the same as the distance to the vertex of the cone. Okay, and that's greater than 1 in particular. So we have the mean curvature increasing from 1 to something greater than 1 as t goes from 0 to infinity. And the next step is to use the faux Harnack inequality to say that it takes an infinite amount of time for the mean curvature to increase from 1 to 1 plus epsilon. So if you fix some 1 plus epsilon here, so that's between 1 and the length of the vertex, then as r goes to infinity, it takes an infinite amount of time for the mean curvature to increase from 1 to 1 plus epsilon. So that means that if you space-time translate, so that the threshold 1 plus epsilon is reached at the space-time origin, then your flows are existing for an ever longer time in the past, which is what you want. because you want to get an ancient solution in the limit. But we can get a limit using the width estimate as we did before. We know that the limit circumscribes the unit sphere due to our backwards asymptotics result. We know that the mean curvature at the space-time origin is strictly bigger than 1. So the limit cannot be a grim hyperplane because it would be 1 all the way through. We then use the Faux-Harnack inequality and barrier arguments to control the squash down between the cone and the truncated cone. But since the mean curvature at the space-time origin is less than, less than the length of the vertex, we can deduce that the squash down is lying strictly inside the cone C. So in particular, the squash down is not a cone. And in fact, a little bit more work shows you that it's equal to what you want. So at each step, all we're using is these barrier arguments and this Faux-Harnack inequality, as long as we normalize the time in the correct way. And that's roughly speaking how the argument goes. So in the last couple of minutes, let me just tell you that, well, for these eternal solutions, you can also analyze the forward asymptotics. So now using the Harnack inequality instead of the Faux-Harnack inequality, you can make some similar deductions as we had in the proof of the previous theorem. So you know that the limit of the mean curvature always exists, could be infinity, but it certainly exists. You know that when you rescale the support functions by t and take t to infinity, you get a limit, you get a relation between the two, you get a limit for the rescaled bodies, and the limit of the support functions is the support function of the limit. So this guy will play a similar role for the forward asymptotics as as the squash down, or if you will, the backward squash down did for ancient solutions. So we call this guy, in a burst of creativity, the forward squash down. And so, right. So what I want to tell you is just this last result, is that if we do take a general convex eternal solution, then we get the same picture. So we get that the forward squash down is related to the backward squash down in the same way that we saw before. So the forward squash down of an eternal solution is equal to this, what we call the x-scribed body of the backward squash down. So you take all of the supporting hyperplanes of the backward squash down, which support the unit sphere, and then you just move them to the other side of the sphere and take the intersection to get this guy. So this is quite a nice result. You can probably guess what the main tools in the proof are. Well, basically the only tools we have, which are barrier arguments and the Harnack inequality. And so just as a final corollary, we also get a rigidity result for translators, which says that if we take an eternal solution, convex eternal solution, whose squash down is a cone, then what we see is that the forward squash down has to be a translate of the same cone. Okay, but then that tells you that the mean curvature at this point, so in the direction of the vertex, is the backwards limit will be the same as the forwards limit by the considerations we had before because of these identities. But because the Harnack inequality says that this mean curvature is monotone, it has to be constant all the way through. And then the rigidity case of the Harnack inequality says that we actually have to be a translator. So that's quite a nice result as well, I think. And I think I'm probably out of time, so I might, there's some more nice results there, but I'll leave it at that.
Great, thank you, Matt. Wonderful. So if anyone has questions, please feel free to post those in the chat or raise your hand. I'll just keep my eye on the participant list. Okay, it looks like the only place where you can't deal with an arbitrary sort of polytope that's inscribed was in this possibility of facets. I guess in the picture you end up saying that if they disappear, if they sort of dissociate from the boundary, they actually have to disappear altogether. So you sort of lose a facet from your
that's right.
Supposed limit.
Yeah, we can't prevent a general circumscribed polytope from degenerating back to a simplex or a regular one.
Yeah.
So if the facets, if enough of them move away, you just end up with a simplex.
Right.
Well, we strongly believe that it should be possible to rule that out using, a more sophisticated barrier argument, but we weren't smart enough.
Right, very nice. Yeah, I didn't know about this construction of eternal solution. That's really nice.
Yeah,
Have you looked at all at the anisotropic analog of this, where you anisotropic mean curvature flows? So I think it's certainly true you can construct analogs of the Grim Reaper, but I don't know, for example, whether you can produce, flying wing analogs and things like that. There's also a question from Glenn. So Glenn, I think you can speak if you like to.
Can you guys hear me?
Yeah.
Yeah.
All right, cool. I don't think I have a video because I'm not technically allowed to communicate on this webinar. Matt, that's beautiful talk and wonderful results. I love them very much. I got some questions, but maybe I just didn't understand properly. So when you say that for each regular polytope, you can construct an ancient solution, is that unique, or are there many that can project down that can be collapsified into a regular polytope?
Fantastic name for the squashdown. Thanks for that. Collapsification, I like it. Excellent question. I definitely didn't answer that question in the talk, and I don't know the answer to that question. So the best we can say is that in dimension, the best result we have is in dimension 2 as well, which says that we know exactly what we have uniqueness of the asymptotic translators. But the uniqueness of, the squashdown just tells you the sort of order T behavior. That leaves open the possibility of having solutions which have the same squashdown but deviate to lower order. So we don't know. Good question.
Thanks. That's really interesting.
Yeah.
Time for one more question?
Go ahead.
Sure.
The last result about the translators having, squash forward or whatever you want to call it, a cone. Is that a characterization?
Yes. So I didn't say it explicitly, but I did hide it there as a footnote. We always assume that we have bounded curvature on each time slice, but that's it. So if you have a convex eternal solution with bounded curvature on each time slice, then if the squashdown is a cone, then it has to be a translator.
And
the converse is true. The converse
is true. Yeah.
The converse is fairly straightforward to see. It's an exercise, but the other direction is the important one. So
yeah, awesome. That's it. I'm done. Thank you, guys.
Very nice. Thanks.
Thanks. Good questions.
Are there any other questions? Don't see any other hands raised at the moment. Okay. Also, I think everybody should have received a note about the coffee break. So when we finished here, please feel free to join us there. Just grab a drink and join us. Good. So, all right. I don't see any other hands raised. So in that case, thanks, Matt, for a wonderful talk, and we'll see you at the coffee break.
Thanks, Ben, and thanks, everyone.
Thank you. I close the meeting. Okay.
See you.
Yep.